Okay, thank you, Nomi, for the introduction. Today, I'm going to talk about our work on cloud exploration of CAZyme annotation in human gut microbiome. So this research has been funded by ODSS supplement grant since last summer. So this supplement is to support our R1 project, which has an objective to develop bioinformatics tools to support or to facilitate microbiome-based predictive personalized nutrition. So our goal is to develop a bioinformatics tool to annotate metagenome sequencing data to predict personalized dietary utilization. So the reason is that, as we all know, that we consume a lot of dietary fiber each day. However, different people will respond to the same diet differently, just because we have different microbiome composition. So we developed a bioinformatics software called DBCAN, which takes metagenome sequencing data as input. So those metagenome sequencing data can be sequenced from fecal sample of different human individual, and DBCAN can predict dietary fiber degrading or digesting enzymes and further predict what dietary fiber that microbiome sample can digest. So as I said, the DBCAN's software tool's name, we developed this in 2012 for its first version. We continued to improve that in 2018 and 2023. So what this software does is that it takes bacterial genome or metagenome or context as input. It predicts carbohydrate active enzyme or CAZyme, and also the gene clusters. Shown here is the gene cluster that contain not only those enzymes, but also transcription factors, transporters, and segment transduction protein. So this software tool eventually or essentially can predict the glycan utilization in microbiome sample, as I mentioned. So it is offered as a web server and also as a standalone software package on GitHub. As you see here, our web server process on average 40,000 jobs from users all over the world per year, and the standalone software package has been downloaded over 10,000 times, and the paper are highly cited. But what I really want to introduce today is about the supplement grants, where we developed a comparison work. So we are seeing an increasing number of jobs submitted to our website. So the website has been hosted on this standalone desktop server since 2017. It has just 32 CPUs, 128 gig RAM. So with this supplement grant, we implement this website also on Amazon Cloud, the AWS. At the same time, we also try to compare the website that we implemented on our university's high-performance computing cluster called HCC, our standalone desktop server called BCB. So in order to compare the computational efficiency of these three web service solution, we use E. coli as the input to the three websites. So here shows the performance comparison of these three solutions. So basically, we submitted 1, 5, 10, and 50 concurrent jobs to these three websites and evaluate how much time, the runtime that can finish those jobs. So for AWS, we use one EC2 instance to host the user interface, but the actual web submitted jobs are managed by AWS Fargate service, which can automatically allocate computing resource on demand. So for HCC solution, so we have one computing node that has a similar number of CPU as our standalone server, BCB. As you see here, with the concurrent job increases as expected, the two on-prem solution, BCB and HCC, has an increasing runtime. However, for AWS, this is not the case. You can observe here with 50 jobs concurrently running on AWS, we actually have a smaller runtime compared to a smaller number of jobs. So basically, our conclusion from this supplement project is that the two on-prem solutions are more efficient to process a smaller number of jobs, but AWS solution offers more competitive performance when more jobs or large number of jobs are submitted concurrently. So I want to stop here and thank you for your attention. I don't know if I have time for questions, but thank you.